So last time, in the last lecture, we saw what are breadth first search and depth first search, and like a qualitative idea or the general idea of what they mean, BFS and DFS. And in this lecture, we will get into more of the nitty-gritty of how to implement those. That if you're writing a program, if you're trying to implement them, then how do we go about doing that, and how much time do they take? Okay. So this lecture is going to be about implementing BFS and DFS. All right. So since they are graph algorithms, let's first talk about some. So first, let's just compare some running times. So let's look at a graph. So a graph G is equal to V comma E, and we'll usually represent V as N and number of vertices as N and number of edges as M. Okay. So of course we want to have polynomial time algorithms. In M and N, because they are the input size, but because N is the number of vertices and M is the number of edges. But how do we compare two such polynomials? For example, suppose you have one order M square algorithm versus order N cube algorithm. Which one is better? Yeah, Harsh, you're saying something?
Order n cube is better because M is order n square.
So, which one is better?
Sir, it depends whether the graph is dense or sparse.
Yeah. So it depends on the whether the graph is. You're right, Harsh, that M is order n square, but M can be much smaller than n square, right? It can be order n also, for all we know. So if the graph is sparse, then this will turn out to be n square, and this will turn out to be n cube. So this will be better. But if M is actually theta n square, let's say, then this will be n to the 4, and this will be n cube. So this will be better. So it will depend on relationship between M and N. Okay. So, but for a connected graph, we know that M is n minus 1, right? Why? Because if number of edges is less than n minus 1, then the graph is disconnected. And M is at most n choose 2. Because the number of edges in a graph is at most n choose 2, right? So what we will actually aim for, or what is actually linear time, is order M plus n. Okay? So we'll call this linear time. And this is equal to order M if the graph is connected. And why this is okay? Something wrong. Yeah. And why this is equal to order M if the graph is connected? Can somebody tell?
Because n is order n.
Yeah, because n is, or M is greater than or equal to n minus 1, so n is less than or equal to m plus 1, so n is order m. Okay, and then we can apply one of the rules that we discussed in the asymptotic notations class to say that, okay, this is then order m. Okay, good.
Sir, which algo did you say will work better for sparse graphs?
Sparse graph order m square will work better, right?
Yeah. Yeah.
So I mean, depends on how sparse is your sparse. I mean, so if you say linear number of edges is sparse, then yes, of order m square will work. So I mean, sparse is a very generally linear number of edges, or up to n log n. Also, some people call that sparse. So I mean, it depends on your definition of what you call sparse. Generally, linear is considered. So then m square will be better. Okay. Okay, good. Now another question that we will address is, okay, so we are going to do some graph algorithms, right? So we need to have a representation of graphs to do that, right? So how do we represent graphs? And this you must have seen in your data structures and algorithms class, but I'm just going to repeat just a bit. So question is how to represent graphs. So there are two basic ways. First one is adjacency matrix. Okay. So you have, if suppose v is equal to n and v is equal to 1 to n, just for sake of simplicity, then what is it is adjacency matrix is an n cross n matrix A such that Aij is equal to Aji is equal to 1 if Ij belongs to E and is equal to 0 otherwise. Yes, so I'm just repeating this, you know, that if there is an edge between u and v, suppose v is the ith number and u is ith number, v is jth number, then you put 1 at the ijth place and jith place. So this is going to be a symmetric matrix. Yeah. So now, if you are given an adjacency matrix of a graph, so you are given this representation now. So you have a matrix, a square matrix, and then you have this adjacencies which are encoded as the matrix entries. Then now, if you are asked to check whether an edge exists in the graph, then how much time will it take? Yes, Ayush?
Constant.
Constant time. Constant time we'll write as order of 1 time, right? So order of 1 is any constant, right? Okay. How much space does it take?
N square.
How much space does it take? Say again, sorry.
N square.
N square.
N square. So more like theta n square, right? It is not like order of n square, but theta n square because it will take n square space. You cannot do it in less than that. Okay. And also, if you want to check, go through all the edges incident on a vertex. Then it might take, or it would take, theta and tan. Because you have to go through the whole row, right? Good. So these two are the problematic aspects of adjacency matrix. This is good that you can check in constant time that whether an edge belongs or not, to the graph or not. But it takes too much space, and for every vertex, if you want to go through all its edges, so even though a vertex might have very less edges, so a vertex has only 3 edges, but still, if you want to go through all its edges, you have to go through the whole row. Okay, so that is the problem with adjacency matrix. And so the other thing is adjacency list. Okay. So in adjacency list, what do we have? for each node in like the vertex set, we have list of neighbors of V. Okay. And let's say that is adjacent of V. Okay. Is list of neighbors of V. So for each vertex, so for so adjacency 1 will be list of neighbors of 1, adjacency 2 will be list of neighbors of 2, and we are not specifying any order here. So they can be in any order, right? Now for each edge, let's say ij, it occurs twice. Once in, I mean, so what do I mean by an edge occurs twice? That if you want to, like, look at the edges, or if you want to infer what are the edges, then this edge can be inferred in two ways. Once in adjacency of I, j will come, and again in adjacency of j, I will come. Right? So each edge will come exactly twice. So what is the total length of all the lists?
2m.
2 times n, right? So this you must have seen. This is you can also do it as, like, summation of degree of V for V belongs to V is equal to 2m. So you can infer it in any way, but the takeaway is that the addition, if you add the length of all the lists, you get 2m. Okay. And then now suppose you want to initialize all the lists. Initially, all the lists are empty. So maybe you get order n space, even if the vertex does not have any number of edges, for initializing the list. So total spaces, order m plus n. So this m plus n is that suppose you have an empty graph, you don't have any, still you have these empty lists, and still you have n number of lists which do not have any neighbors. None of them have any, the lists are empty. So still you are consuming order n space in that case. So that is why order m plus n is the total space taken, right? Because initialization of the list will take order n space. Good. So total space is order m plus n. Now this, of course, is at least as good as order n square. Why? Because m is less than or equal to n square. I mean, n choose 2, but let's just say n square. Right? And now to check, okay, let me pull this down a bit. Yeah. So good. Now to check whether an edge UV is present. Okay. How much time will it take?
Order M.
Order M, you're saying, or N? Sorry.
Sir, M.
N. Yeah, order N is bound. That's correct.
Order
But
N.
can I get something better?
Theta degree of V.
Degree of U or V.
Yeah, exactly. So let's say big O. We want an upper bound for now. So because we might find it before also, so it's okay. So order of degree. So I'll use D of V to represent degree of V. Okay, fine. I don't know what I what I achieved by writing dV and degree of V, but degree of V will be written as D of V. Okay. And I hope you are familiar with the concept of degree and neighbors that I had asked you to revise in the last lecture. So order of degree of V or order of degree of U. Okay, good. Depends on which one you go for. So order n in worst case, of course, because the degree is bounded by n minus 1. Good. So this is like the adjacency list is actually a very natural notion of graph exploration. So why? Because you just
Excuse me,
want.
sir.
Yeah.
So like in what applications is an adjacency matrix useful? Like isn't something like a set of all ij pairs, something like that, a better way to store?
Say again. Sorry.
A set of all
A
ij
set of
pairs,
what?
ij pairs like node pairs, ij, node I to node j,
Set of
an unordered set of all such pairs.
ordered set of all such pairs. No, I don't
Unor-
understand. So I have a set of vertices. I have a set of edges, and then what are you saying? How do we
so
represent that? I am not getting.
so like I just store all the edges in an unordered set.
But how are you going to access that set? So set all so you need some data structure, right? So matrix has a like two-dimensional array data structure, so it can be just like you can go directly there and find out that okay whether this edge is present or not. So if you keep it an unordered set, then you might have to go through the whole set to find out whether an edge is present or not.
So actually we can find in constant time, I guess, in an unordered set.
In an unordered set. So again, but you need to use some data structure for that.
Yeah.
You'll use some union find or something like that.
Yeah.
Yeah. So again,
We'll use a hash table.
that data structure. Yeah, I mean again, so you can hash table again, like so they will require slightly more space or something. So again, you can find these things, but these are the like very natural ways, very like what to say, very simple ways, let's say, to represent a graph, which do the job. And actually, you cannot get much better than because in the worst case, you will have to store all the edges, and there are n square edges. So, what do you achieve by putting in an unordered set?
So like for sparse graphs, it would be much better in terms of space.
But sparse graphs, we already have the adjacency list.
So like adjacency list, it does have other drawbacks as compared to adjacency matrix, right? Like
the only drawback is that for finding an edge, whether it exists or not, you have to go through all the
yes, and like
neighbors of.
like finding all neighbors of a vertex
That's all.
also.
Huh?
Like finding all neighbors of a vertex also, like even for that. Sorry.
No,
I mean like
finding. No, just if you want to find whether a particular vertex is neighbor of another vertex, then you need to. Sorry. Yeah, I mean that's what takes more time. So you are given two vertices, and you want to. So basically, given an edge, whether that exists, or not, that's what takes more time. Okay, yeah, you can think about it, a bit offline and see whether, like, is if there is any actual improvement in going through an unordered set. Okay, and if you have any questions, you can take it up here.
Sure. Thanks, sir.
Okay, good. So what I was trying to say, the last point that I was trying to say was that adjacency list is a very natural way of representing graph if you want to explore graphs. If you don't already have like some operations that you want to perform on graphs or whatever. You are just wanting to explore that. Okay, you don't know what is there, and you just want to see that. Okay, you go to one node and you see, okay, what are its neighbors? Okay, these are its neighbors. Let's go to one of their neighbors. So you can go to their adjacency list and then perform explorations more and more. So natural representation for exploring graphs. So one thing that you can try, Shravan, is after we do this BFS and DFS implementation, you can try doing these with your favorite or whatever you're trying to come up with the whether you can do BFS, DFS sort of things with that representation easily or not. That might answer some of the questions that you have. Okay. Good. So yeah, this is one thing that this is a natural for exploring graphs. There is another thing that we will be using is two data structures, which is queues and stacks. Again, you must have seen these, but I'm just going to queues are first in, first out. Stacks are last in, first out, right? And you can implement them as doubly linked lists. Okay, and with 2 pointers basically. And what are queues? You add at the end, and stacks are add at the beginning, and then remove also from the beginning, and so on, right? So if a new element comes, it gets added at the beginning, and then that's what you do. Okay, good. So now we come to BFS. Okay, let me make slightly more space. All right. So let's come to BFS again. So BFS, what were we doing? We started with one node, and then we looked at its neighbors, and then we look at their neighbors. So this was level 1, this was level 2. So for them, we will have the list level I, and we start with level 0, which will just contain S initially. Okay. And then we also have this discovered thing, discovered a list. So discovered V is equal to true if V has been discovered, otherwise it is false. So we initialize this with false for all V. And when a V is discovered, then whenever a V is discovered, then we add V, make this value to be true. Okay, so these are the two lists that we'll maintain because we want to have the BFS tree also. So let's look at the algorithm. So since I would have just typed the whole thing anyway, I have just copied the image from the book. So this is from the book, the algorithm. All right. So let me just switch off the fan. Just a moment. Okay. So yeah. So this is the BFS algorithm. Okay. So let's just look at it slowly, step by step, that what it is doing. So you start with the node S. S is the starting node. So this BFS will actually compute the connected component containing S. All right. So set discovered S is equal to true and discovered V is equal to false for all other V. This I already said above that S is discovered, no other vertices are discovered. Initialize L0 to consist of a single element S. So L0, as I said, is just S right now. Now set the layer counter to be 0. So this is the layer counter that will increase. Okay. Then set the current BFS tree is equal to empty. So your tree is currently empty. Now while Li is not empty, so initially Li is not empty. Initially Li is L0, which contains S. It has just one element, right? Now you initialize an empty list L1, let's say. And for each node, U belongs to Li. So right now, I is 0 only, right? So for each node U in Li, that means for only node is S right now, consider each edge incident to U. So look at, sorry. Yeah. So look at all the neighbors of S. So this is S. Look at all the neighbors of S. Let me draw it here. So this is S. Look at all the neighbors of S. And for each edge, now this is V1, this is V2, this is V3. If discovered V is equal to false, if V1 is not discovered, so in the first, like for L1, none of them are discovered. Set discovered V is equal to true. We in the discovered array we set this value to be true corresponding to this particular vertex, and then we add this edge. Sorry. We add this edge to the tree. Similarly, now we look at the second edge. Again, discovered this is false. So we set discovered V2 to be true and add this edge to the tree. Then we look at the third. And then we add we also add V to the list Li plus 1. And we add V to the list only if it is not already discovered. So all these three were not already discovered, right? Fine. So let's just, and then we end the if. And then we end the for loop also. This one. For if. Okay. So we end the for loop also. That is for each node what we were doing. And then we increment the counter by 1. So let's just look at another iteration of this. So suppose, why is this happening? Suppose now V1 had some neighbors. V1 had this neighbor, this neighbor, this neighbor, and this neighbor. Okay, let's not do this to be. Let's take it to be. Okay. All right. So now you come to L1. So you increment the counter I by 1. Your I is equal to 1 now. Okay. And now you go for the while loop. So Li is not empty. Now L1 has 3 vertices. V1, V2, V3. Okay. So now L1 is not empty. So initialize an empty list L2. Okay. So right now it's empty. We'll add vertices. So let's call them V4, V5, V6 for now. Okay. So L2 is empty right now. And for each node U in Li, so I is 1 right now. It has changed to 1. So for each node in Li, that is V1, V2, and V3, consider each edge UV incident to U. So let's just take the first vertex V1 here and consider all edges. So it has 4 edges, 5 edges incident to it. One is to S itself, because in the adjacency list there will be 5. Since its degree is 5, there are going to be 5 edges, which will be, or 5 vertices in the adjacency list. So S, okay, fine. Let's look at S. Discovered S is false. No, discovered S is true. So we'll forget about S. Okay. Then we look at, suppose V3 comes first. Or, okay, let's say V3 comes later. Then comes V4. So discovered V4 is false, right? So we put discovered V4 is equal to true. So we put discovered V4 for this true. Add this edge to the tree, this V4 edge to the tree, and add V4 to the list Li plus 1. So here we put V4. Similarly, we will add V5, we'll add V6. But what happens when V3 comes? Again, discovered V3 will be false. So we will not add it to the list or do anything. Now, for each node U, we had to do this. So first we had considered V1, now we'll consider V2. And then we'll consider V3. And when we have considered all these vertices, then we'll finish this for loop. Right? And then when we finish the for loop, then we increment the layer counter by 1. Okay. Why? Then we increment the layer counter by 1. And then we again go to the next layer. And then we continue doing this. So I hope the idea is clear of the algorithm. I mean, the idea is clear, but even the implementation, that how we are doing this. What we are doing, we go to a vertex, we look at its neighbors, and we add it to the next layer. Then we go to another vertex in the same layer, we add its neighbors to the next layer. We go to another vertex in the same layer. So we keep going through the vertices of a layer till all of them are finished. Till any of them are left, and then we try start to process the next layer. So that is why, the BFS thing, that first we have S, we add all the vertices which are neighbors of S in the first layer. Okay, now we have got the first layer. Now we add all their neighbors in the second layer, and after we get the second layer, then only we start to process the second layer. Okay, any doubt? All right. So now there's just like some small points, and we'll do the running time analysis. First thing is that the list li can be a stack or a queue. Does not matter, because we can process it in any order, right? But the main lemma that we are trying to show is the above algorithm runs in order m plus n time. Okay. So how many times the while loop goes on? Number of layers times, right? But that does not really matter. I mean, so if we just look at, so this is basically order n times, because there can be at most n many loops which can be there, at most n many while. The while loop can run at most l many times, because there can be at most n many layers. But that will give us a bad bound. What is a better way to do this is that each node is in one unique layer. Okay, so each node goes to either for some li, right? And for each node u, what do? We consider each edge uv incident to u, and for each of them, all these things we do. And how much time this arrow thing takes, that I'm set discovered, checking whether discovered is true, then setting the discovered to be true or not, then adding the S to the tree, adding B to the list. How much time all this takes? Whatever I've highlighted with the arrow. This part.
Constant.
This takes constant time. Right? So for each node, for each edge we take constant time. Okay, so for each node, for each edge incident to the node, algorithm takes order 1 time. So total time for each node is how much?
Degree.
Yes.
Degree of.
So, yeah. So let's say total time for a node V is equal to order of degree of V. So total time for the algorithm is equal to summation of V belongs to V, order of degree of V, to order M here, but also then there is this initialization. We first have to put like discovery of V is equal to false for every node and so on. So initialization takes order n time. So total time is order n plus n for discovery, or discovered this array that we have, right? So any questions about this running time analysis and algorithm, BFS? Just like for 1 minute, you can have a look at it.
Or something else.
Sorry, Avdesh, you're not audible clearly. Say again.
Sir, we are using L as vector, L0, L1, L2 as a vector or something else.
Which one? L0, L1, L2?
Yes.
No, they can be just lists. I mean, yeah, arrays.
Okay, sir.
Or I mean queues. Sorry, I mean so we said that it can be either a stack or a queue.
I want to ask that LI such that we are something that now LI is
Sorry, Aditya,
stack.
you are not audible. I
Something.
cannot hear you properly. Say again. Okay, try once more.
Hello, sir. Now am I audible?
Yes, yes, yes. Tell me.
Hello, sir.
Yes, yes, you are. Tell me.
LI is a queue or
A queue or a stack?
yes, sir. Now, generally, when we made an algorithm, then we have to initialize L matrix. L is a vector or array, such that Li is a stack or queue, right?
Yes. Li we are initializing
So,
within the algorithm here.
okay, sir.
Yeah. Okay. So we don't know how many are going to be beforehand. So we initialize them within the algorithm itself.
Sir, iterating through the queue also takes constant time for every node, right?
Iterating through the queue, yeah, I mean, depends on what you mean by iterating through the queue. Just finding the next node in the queue will take constant time.
Yes. I mean,
So
you
you
will not
already have the
explicitly
pointers,
write.
keep moving the pointers ahead. So
Yeah.
from one pointer to the next pointer will take constant time.
Yeah. So I mean, just the while loop, the chunk of code that you marked in violet, while to end while, that itself takes order n plus n time, not just order n.
Yes. The while li is not empty, initialize the empty list for each node. Yeah. Sorry, wait, why that will take order n? Because Yeah, I mean, it should be, but I don't see why it will, because you have to, yeah, because you have to look at the discovered V for all the nodes and so on. Is that the reason why you're saying, Anshuman?
No, like for each node U in Li, you will
Yes.
be going through Li. So like that also contributes order one time for each node U, right?
Yes, that's correct. Yeah, of course, for each node Li, you will need to, at least go to that node and look at this. So yes, this will take order one time, and since we have to do that for every node, you will take order n time for that also. Good. Yeah. Okay, so this I hope is clear now. Any other question? Quickly.
So could you explain the time complexity of the while loop? How it came to be O of n?
How it? No, so it is not O of n. It is actually O of m plus n. So O of m I have explained because of the degree, because of this, that for each edge, for each vertex, this thing will take order of degree of vertex time. This whole thing, because this takes order one time, and we do this for each edge, right? So this will. This
Yes,
is
sir. For actually, I was confused about how we came to the n portion of the algorithm.
portion. So what Anshuman was pointing out was that this for each node, which is U in Li, we have to. So Anshuman, there is another like small like point there, that this n is actually will be happening only for the vertices that come in the list.
Yes.
So not for those who which are not in the like connected component which contains S. So it might not go till n.
Right.
It might only go till the number of vertices which are in the connected component in the S, right? And that is then again going to be at most m.
N.
No, I'm saying at most m is the number of edges that is going to be traversed by this algorithm. So that
Yeah,
n cannot be
HSM.
more than m. That's what I want to say.
Yeah, okay. Yeah, right.
Sir,
Yes.
sir,
Yeah.
Understood.
sir, if there are more than one connected component, then we have to do this traversal for every connected component.
Exactly.
So that's why
Exactly.
we order it like
So
that.
if there is more than one connected component, then you have to keep picking vertices and yeah, do that. So who had asked the question before? Vinay, was it you or was that somebody else?
Sir, I had asked the question. It's
Yeah,
clear now, yeah. It's
it's
clear.
clear? Okay,
Yes, sir.
thank you. All right, so let's now quickly go to DFS. We spent quite some time on BFS, so let's see what DFS does. Good. So let's come to DFS. So idea is to use a stack when we discover so the main thing is that there are two things. One is discovery and one is exploration. And exploration. So what happens is that in in BFS we keep discovering the nodes, first we discover all the nodes which are in a layer, and then we start like exploring those nodes and discovering new nodes from there. So BFS, so first discover all the adjacent nodes to a vertex, and then explore them. And in DFS, what if we discover a node, that is not explored, we want to immediately explore it. Right? So this is the main idea, like, if you want to say it in, like, language terms, that in DFS you go to a vertex. Okay, so this I have not seen before. So okay, let's go to its another neighbor. Okay, this also I have not seen before. Let's go to another neighbor instead of looking at all the neighbors that they have. Okay, so this is the one very basic difference between like DFS and BFS. Okay, so now this is what we want to implement. This is the basic idea of DFS, that okay, if we reach a node that we have not explored before, then we want to explore it immediately. So how do we do it? So how to implement this idea? Keep a stack. Okay. And while exploring a node U, add all its neighbors on stack. Okay. And then like look at the first one and go explore that. Explore the first neighbor, the first one on the list, on the stack. And then again, you will do this recursively now, as we had seen that, okay, now you will look at its neighbors and then you will put that on the stack and so on. So when we look at the algorithm, then it will become more clear. So we'll use a list explored V, just like we had in discovered V in BFS. So this is false initially for all the vertices. Okay, good. So let's just look at the algorithm. So what does the algorithm do? Initialize S to be a stack with one element S. So let's just try to make a stack here. So initially it just has S. Okay, while S is not empty. So right now it's not empty. Take a node from U from S. So now, like, you take S out from the stack. So S is getting overloaded and small and capital, but I hope you can understand. So, okay, let me try this small S. Yeah. So you take out S. Now explode U is equal to false. Is explode U is equal to false? Yes. Initially it's false for every vertex. So let's set explode S is equal to true. That is what it's doing here. And for each edge UV incident to U, so let's just again draw a similar graph. So this is S, this is V1, V2, V3. Let's say something, then something V4, V5, V6, and V7. Okay. So for each edge UV incident to U, add V to the stack S. So now we have removed S from the stack. So take a node is like, you can remove that node from S. Now you can add the vertices of its neighborhood to the stack. So you can add V1, V2, V3. Okay. Okay. So first you don't do that. Slowly. So all right. So now take a node U from S. If explode U is equal to false, then you set it to be true. For each edge, you added V1, V2, and V3 to the stack. Now end for. So this for loop has been finished. That for each edge you have done this. Okay. Now you come up and use end the for, then you end the if also. Now you look at the while loop and see that, okay, S is S empty? No, S is not empty. So now take one node. So you take V3 from the stack. Okay, so now this U is V3. Is explode V3 false? Yes, V3 has not been seen before. So you put explode V3 to be true. Now for each edge incident to like you add V to the stack S. So each edge incident to V3. So V1, V3. So what are the edges incident to V3? Okay, so I should have put maybe some vertices here. Let's say V8, V9, and V10. Okay. So now V3 has 4 edges. So let's say S, V4, V8, V9, and V10. And V3 can be removed from the stack. Let's say. So now you added these to the stack. Now it comes to V10. The next time the loop iterates, then this U becomes V10. And then you go down. And then when you come up, then you have explored V10. Then what is the last thing left? Then you have V9. So then you will explore this. Then you have V8. Then you will explore this. Then after you have finished all these, then you will come to V2, which is here. Okay, and then you will explore this whole tree which is below V2, and then you will finish this V2 tree, then you will come to V1. Okay, so this is how this will work, and so you can see with an example that how this works. So the idea is that once you look at a node, you put all its neighbors in the stack, and then you take from top of the stack. So one thing is that if the adjacency list is in some order, then as we saw that here we added V1, V2, V3, but first we looked at V3. So the exploration order reverse of the adjacency list. Right? And then again, let's just look at the time that it takes. That for each node, again, it looks at here. This will take degree of U time, right? Because this takes constant time. And this also takes constant time. So for each U, it takes degree of U time. So again, the running time is summation degree of U. U belongs to V equal to order. And again, because of initialization, etc., we have order n time. So total time is order m plus n. So here the main thing is in DFS is that you go to a node, and if it has not been explored before, so there can be the case that this node has been explored before. But then what do? You just don't add its edges to the stack. So one vertex can be added many times on the stack, like S is being added here again. No, sorry. Set explode. Yeah, S is being added again, but that does not matter because it is explored already. Right? So we will see some applications next time. I'm slightly over time. But you can look at these algorithms with some examples. And if you have any questions about DFS, you can ask right now.
Sir, I couldn't understand how are we like calculating the time for initialization here in DFS.
Initialization, nothing much. Like explode V took false for every vertex initially.
Okay, got it.
There are n vertices, so it will take n time. Order n time. Okay, so like the idea is like, again, it's not very, so you have some S, you have some vertices. So the idea is that you take S, you add all its neighbors on the stack. Then you look at its, pull out the first guy, look at its neighbors, put them on the stack. Again, pull out the first guy and keep putting them on the stack. Then you finish that, then only you can go forward. Okay? Any questions?
So how are you determining the number of times the while loop will run?
How are we determining?
The number of times the while loop will run.
A number of times the while loop is, because explode while S is not empty. So the thing is that once a node is taken out from S, then its explode will be true. So number of times the while loop. So we are not really doing number of times while loop, because that will again give a worse bound. So what we are doing is that we are looking at the inner thing and we are determining its complexity.
Okay. No, so that
So the thing is that how many things can get added to the stack?
Yes,
So
yes.
and that can get added only if an edge is considered, and that gives a bound order m, because there are m edges. Just means we have already that. I will not.
Won't the while loop run for n times? Like in every iteration, one of the node is popped from the stack, and like none of the nodes gets pushed into the stack twice. Like once it's visited.
It will run the number of nodes which are there in the connected component times.
No, the while loop, like the number of iterations for the while loop will be n times, right?
N depends what is n. So
like the graph is connected.
The graph is connected. Okay. So if the graph is connected, then yes, it will be n times, but that is a bad bound, because I mean that is fine. It will be n times that it will run for each vertex. Something will happen, but the inner thing is the main thing that needs to be considered.
And even in general, like even if the the graph isn't connected, like we run DFS for different nodes, like
yeah, that is a separate thing. Right now we are just looking for S.
Yeah, okay.
Yeah. So yes, it will run n times, and for each of the vertices, then it will run degree of times the for loop. Okay, Shub?
Yeah, got it. Thank you, sir.
And Rishi, your question, I think Nikhil has answered, that we are removing V from the stack. Take a node U from S means we are removing V from the stack. Rishi?
Yes, sir. Got it.
Okay. Good. So yeah, we are almost like, yeah, some of you might have another class after this. So thank you for coming today. And if you have any other questions, like, you can ask on Piazza and or in the next class. And we'll be covering some applications of BFS and DFS in the next class. Okay. Thank you.